Yeah, today is the lesson 2 in the Python 200 series. Thanks for joining. And today we'll discuss about introduction to machine learning and linear regression in detail, right? So what is a machine learning? Does anybody want to explain what is a machine learning? No? Okay. So so this is the whole artificial intelligence spectrum. Within artificial intelligence, we have machine learning. It is a subset of artificial intelligence. So machine learning is basically we provide the data to the machine and it'll go and understand the data and try to predict the output for us. So we are not providing handwritten rules to machine, but we are providing the data, large amount of data to the machine, and it'll go and identify the patterns in the data and then try to come up with its own rules. And once the training is done, and when we give a new input, it'll try to predict the output. So this is, in general, the definition of machine learning, right? So within machine learning, we have deep learning. So, so deep learning is a concept where there is a huge amount of data, and machine learning won't be able to handle the huge amount of data. Basically, the classic machine learning. I'm talking about linear regression, classification, and logistic regression. So when there is huge amount of data, classic machine learning won't be able to train well. That's where we require deep learning. So in deep learning, there are neural networks, and so there are connected neural networks. It's not one layer. There are multiple layers of neural networks in the deep learning, and the data goes through multiple layers of neural network in order to predict the right output. So that is deep learning. It is a subset of machine learning. Okay, and then we have generative AI. Generative AI is where it generates the content, right? If you know about LLM or ChatGPT, it is constantly trying to predict the next word. If you write two words, it will predict the third word. If you write three words, it will predict the fourth word. So, so LLMs are trained to predict the next word. Basically, sorry, generative AI. Um, they generate content. They try to predict the next word in generating the content. Okay, and large language model is basically a machine learning model, but trained on huge amount of internet data. So that is large language model, right? ChatGPT is an example of large language model, right? So this is the whole spectrum of artificial intelligence and machine learning. And yeah, as you can see over here, it learns from examples, not from explicit rules. Think about a situation where there is no machine learning, but I gave you a picture of cat. You need to write some program, and the program output should be whether the picture I gave you is cat or not. So how do you write it without machine learning? Just think through this, right? We need to write some conditions saying that if the image has four legs and if the image has fur and if the image has two eyes, one nose, etc. So we are basically writing conditional programming in order to understand whether the image is cat or dog without machine learning. But with machine learning, we are not giving all these rules or conditions. We are giving hundreds or thousands or even millions of cat images to the machine learning model, and it will create its own rules in order to predict the output, right? So yeah, and in machine learning, there are three types of learning: supervised learning, unsupervised learning, reinforcement learning. So supervised learning is where we give the labeled data to the machine learning model. So labeled data is where it will have an input and output. Let's say we have to train a model on a housing data. Let's say the data set we have is square feet, size of the house, and the price. In this example, square feet is an input feature, price is an output feature, right? We are giving input and output to the model. So that is basically called a labeled data. And we give data to the model, the labeled data to the model, then it gets trained. Once the model is trained on the trained data, then we give test data to the model and then test the model if it is predicting well or not, right? So that is supervised learning. Supervised learning, we have labeled data. Within supervised learning, there are two techniques. One is regression, the other one is classification. So, so regression is where it will predict continuous output and it predicts in numbers. One example I already gave you is predicting a house price based on the square feet size of the house. And the second example is predicting the temperature of the day, right? So in terms of predicting the house price, the predicted value or the output value from the model can be a range of values. It's not one value always, right? It's a range of values. It may be from 200K to 1 million. So that's where we need to use regression. If the output is continuous output and number, then use regression. And if the output is a category, means you know the set of values in the output. Whether, let's say, we have to predict if an email is spam or not, then the output can be spam or not a spam. So that's a category output, right? We know the output. Output is definitive and known. So for those examples, we use classification technique. So that's about supervised learning. And then we have unsupervised learning. Unsupervised learning is where the data is not labeled. We just have the data. It's not labeled, right? That is called unsupervised. When we have such a data, we use unsupervised learning. One example of unsupervised learning is clustering. Clustering is where it'll group the similar data values. Let's say you have a Apple News application, and Apple News application segregates the news based on entertainment, based on politics, right? Based on sports, etc. but the source of the news is from different vendors, I would say, right? It can source from different news agencies, but all the news are sourced and then they are segregated based on category. That's one example of where clustering can be used. It'll read through all the news, and then if a news contains a sports word, then it'll segregate under sports section, cluster or under sports section, right? So that is basically called clustering. So that's one example of unsupervised learning. And then there is reinforcement learning. Reinforcement learning is where the agent will give the output based on the environment, and the customer will tell, or the user will tell, if the output is a reward or not. If the output is reward, then the agent enhances the environment basically to predict the next output right. Let's say the output is not reward, then agents records that response from the user and then try to improvise by itself. So this is called reinforcement learning. If you have used Gemini anytime, if you ask a question, sometimes it will give you two answers and tell which answer you like, and it'll ask you which answer you like, right? So I got those examples, and I used to put a thumbs up to the answer which I like. That's one classic example of reinforcement learning. Okay, and you can see over here, linear regression is to predict the temperature. Classification is to predict whether the climate is hot or cold. In regression, we are predicting a number. In classification, we are predicting a category. Okay. And this is an example of clustering. The related values are clustered. And clustering is obviously unsupervised learning. Okay. So any questions until now?
Can you explain k-means? What does that mean?
Yeah, that's one clustering technique. Um, yeah, k-means is a clustering technique. We'll see if that will be in later screens. Okay. Okay, I'll move ahead. So scikit-learn is a library in Python used for classic machine learning, right? Here is an example of linear regression code. So you create the model, and we are saying we require a linear regression model, and X train and Y train is your data. X is an input, Y is an output, and then you are giving the model both input and output in order for it to train by itself. And then you are saying fit, you are calling fit, then the model is trained on the labeled data. And once the model is trained, we'll ask the model to predict the Y for X underscore test data. So the, let's say we have the complete X data, we'll split it into train set and test set, and we use the train set to train the data, and test set to predict the output or to test the model, right? Um, so I can show you, there is an image. So yeah, our whole data set is split into train set and the test set, and we use the train set to train the model and test set to test the model. Okay. Um,
When we split the data set, it's the same data set for the training and testing, right? It's the just two clones.
um, the data set is the same, but we split it and then we don't expose the test set during the training. We only train on train set.
I'm just trying
Does
to understand splitting. Splitting means like I make a copy, and then one copy goes to the training, one copy goes to the testing, right, of the data set.
no, let's say you have a list of 100 numbers, then you split it by 80/20, right? Um, from 0 to index 79 in the list, you create as a train set. And from index 80 to 99, you create it as a test set.
I see.
You
Understand now.
you
Got it.
split the array. Yeah.
Okay, got it.
So yeah, this is an example code of linear regression with scikit-learn, and so it's the code is the same for all the types of machine learning techniques available for linear regression, for k-mean, and the other machine learning techniques. We create the model, we fit the model on training data, then we predict, and then we evaluate. Evaluate is basically checking how good the model is, right? So sorry. Yeah, this is about the scikit-learn code. And so you can see in this diagram, on the x-axis, I have square feet, and in the y-axis, the price of the home. And this line represents our model, right? And these dots are the data points. Let's say for 1,000 square feet home, the price is somewhere between 100K and 150K. Let's say 140K, right? These are all the data points. Let's say we gave all these data points to our model to train the model. Then model comes up with this line. This line is our model actually. And then you say, you give a new data to model in order to predict the output. Let's say you were giving 2,800 SFT. Then what is the predicted value? It will be somewhere 340K, right? So, this is an example of a linear regression model with one feature. When I say feature, it's an input to the model, right? Here, square feet is a feature. X is an input feature. Y is an output feature, right? And so this is the formula. It's basically WX plus B. W is a slope. X is the feature, square feet, and intercept is the slope, right? So, um, so when you print coefficient, it is saying W is $107 per square feet. For each increase in square feet, the price is going to be increased by $107. That is what the weight meaning. And the intercept is, okay, here the intercept is taken as 0, right? So um, are there any questions in this slide? Okay. So let me Just a sec. So yeah, so this is the program we saw. Um, we created the model. So this is an feature X. We took an array and Y is output feature. And then we are fitting the model for these X values and Y values. And new underscore X is our test set here. So we are predicting the value for the test set, right? And this is for linear regression. And if you have to do unsupervised learning, one example is k-means clustering. So if you have to do k-means clustering with scikit-learn, it's almost the same code. You were taking k-means model, you were saying convert the data into 3 clusters, and we are saying fit, and then again saying predict, right? So this is an example of k-mean clustering. So if you give, so the data doesn't have a label because it's unsupervised learning. Clustering is a technique of unsupervised learning, right? And it basically clusters the data at the end. So, and then, um, as I said, in the linear regression, the formula is, let me pull the formula here. Um, let's see. Yeah, so this is how we split the test and train set. Here we are saying 0, 2 means 20% of values are taken as a test set. Remaining 80% are taken as a train set. And then we pass train set to the model. Okay, and then all good. We have the data, we split the data, then we fit the data on the model, then we predict it after the model is trained. But how do we know if the model is trained really well or not? We need to evaluate the model, right? In order to evaluate the model, we have this parameter called root mean squared error. So it basically gives the error of the model. Ideally, the error should be 0, right? That's what we look for. And so this is how you get the root mean square error. You will call this mean squared error function. You provide y test. Y predicted is our model prediction of output, and y test is the actual values of the output. We are giving the actual values of the output and our model predicted values in order to calculate the root mean squared error, right? Um, and then we can look at root mean squared error to see how well our model is performing. And R2 is another score. This is how you create an R2 score. You call R2 underscore score function. You provide y test and y predicted. And we'll talk about R2 in a bit. But for you to give an understanding on root mean squared error, right? So you can see in this diagram, this is the actual value, but our model predicted the value is this one, right? The distance between these predicted value and the actual value is taken, and then the average, it's squared basically. So the distance between the predicted value and the observed value, the actual value, is squared, right? The difference is an error, and we square the error and then get the average of all the data points. That's called root mean squared error. Okay, and it should be close to 0. Right, and R2, the formula for R2 basically measures how better the model than simply predicting the mean price, right? If you see here, let's say this is our model. In this example, whatever the square feet is, the price is 250K. Let's say you were giving the model 3,000 square feet. In order to predict the price for 3,000 square feet home, it'll give it as 250. If you give 2,000 square feet, it'll give it as 250. If you give 1,000 square feet as an input, it'll give 250 as an output. That means what our model is doing, it's giving the mean of the data as an output. It's basically underfit, right? So with R2, what we are trying to figure out is how well our model is fitting the data compared to the mean value, right? So this is the formula for R2. It says how better the model is than simply predicting the mean price every time. So this is R2. So we use two measures in order to measure our model. One is root mean squared error. Root mean squared error should be as less as possible, and R2 should be as close to 1 as possible. Okay, and R2 of 1 means perfect prediction, and R2 of 0 means model doesn't do better job than just guessing the mean value, right? So yeah, so so is that clear? Any questions? So yeah, as I said here, the price is basically slope times square feet. Slope, let's say slope is W. I said earlier Wx plus B, right? B is an intercept, W is a slope, square feet is a input feature, basically X, right? Yeah, I think we, as mentioned here, 107 per square feet. For each increase in square feet, the price is going to be increased by 107. That is what weight means. The slope means. Um, so so 80-20 is the split I mentioned. And yeah, and we discussed about root mean squared error. Um, so with one feature means only square feet as X and the price as Y. With only one feature square feet, the R2 is 0.75, right? So then let's say we are adding one more feature. It's not one feature now, we are adding one more feature, that's distance to the input, right? And when the distance is added, and when you print coefficient, right? 107
I'm
is the
sorry,
pricing.
distance, what distance from what to what?
Yeah, so
From the city. I see. Thank you.
yeah, from the city. Let's say the distance of the home from the city is 1 mile, then the overall price is going to be increased by $2,498. If the
Mhm.
distance is 2 miles, it'll be
Mhm.
2 times 2,498. Um, so with the addition of one more feature called distance, our model is performing better. Its R2 is 0.89. I mentioned R2 should be as close to 1 for the best model, right? So from R2 came from 0.75 to 0.89 after adding one more feature called distance. When it is having only square feet as a feature, it was at 0.75. Okay. So this is basically an example of multiple regression. When we give two features, it's an example of multiple regression. So with one feature, the formula is slope times square feet plus intercept. Can you guys guess with two features what will be the formula? Here the slope is 107 with one feature. And yeah, any guesses? With two features, we added a distance as a feature, then what would be the formula?
Square.
Multiply. Oh, sorry. Rafani,
No, no.
go ahead.
Thank you, Irina. I think it will be slope by sum, or in square slope in square something.
Okay, yeah. Any other guesses? I'll tell the
Just
answer in a bit.
multiply slope, square feet, and distance.
Yeah. So
Oh.
it'll be, yeah, slope times the square feet plus slope times, actually slope 1 and slope 2. Now there will be two slopes, right? Slope 1 times the square feet plus slope 2 times distance plus intercept. Okay. So so yeah. Um, so the slope for square feet is 107. So 10 times square feet plus 2498 times distance in miles plus the intercept. So that's the formula with two features. And let's say we are adding one more feature. It's a feature of whether the home is a new home or an old home. If it is a new home, our data set will have value 1, older home is value 0. With this new feature, this is a third feature we are adding. Then R2 is even improved from 0.89 to 0.94. That means our model is predicting well. Our model is basically improvising in order to predict the right house price, right? So, and if it is a new home, the weight is 27,500. So the new homes will cost 25,500 more than the old homes. So that's the idea. Right. So that's how we look at the data. We see which feature basically improves the model performance. Then we consider those features. Let's say there is some feature. Let's say there is a there is an apple plant in the home you are trying to buy. And if you're considering that apple plant as a feature to your model input, the buyer is not going to increase the price because of the apple tree, right? So that feature is basically is a noise to the model. If you consider apple tree or trees in general within the house as a feature in order to predict the house price, then that's basically noise to the model and your model is not going to perform well. So those kind of features we exclude while training the model. So you should be smart enough to include features which enhances the model performance. Okay. I think I see. Okay, so the formula with two features is let's say I told a simplified formula, right? Wx plus b. W is weight, x is the feature itself, plus b is bias or intercept. So if we have two features, then it'll be W1 x1 plus W2 x2 plus b. If it has three features, then W1 x1 plus W2 x2 plus W3 x3 plus b. Okay. And there is a concept of overfitting. Okay. So let's say in this diagram, our model is this line. And obviously our model is not predicting well. Let's say for 3,000 square feet home, what is the actual price? It's somewhere around 350 or 400K. But our model will predict as 250K. That means our model is not predicting well, which is called it's underfit. Model is underfit. Okay. This is an example for model is underfit. And over this image, this is the best fit the model can do based on what we can see, right? So this is a perfect fit. And there is an overfit. Overfit is where, yeah, you can see this is an example of overfit. Overfit is where a model is little biased towards the training set. It will perform well on the training set, but on the test set, it won't perform well. That's an example of overfitting, right? So until now, we talked about linear regression models, right? There is a polynomial regression as well. Polynomial is where the formula will have order, like W1 x square plus W1 x1 square plus W2 x2 plus b. So here we have x square. That's a two-order polynomial. So if you are increasing the order of polynomial, the model is going to overfit sometimes. So that's, you can explore more on the overfit, but on the high level, this is the concept of overfitting. Okay. I think that's all for today. Yeah, we looked at scikit-learn, how to create the model, fit the model on the data and predict on the test set. Then we looked at root mean square error. And then R2, these are to measure the model performance. R2 should be close to 1 for a best model. And root mean squared error should be close to 0. Right? We know train and test split. Usually it's 80% of the data we consider as a train data, 20% of data we consider as a test data. And then multiple regression, basically where we increase number of features to see how the model is performing. Right. And then we talked about overfitting. That's all for today. In the next lesson, we talk more about classification. We talked in this lesson about linear regression. And the next lesson, we talk about classification. And then logistic regression is a technique within classification. And then there is a KNN classifier. It's a K nearest neighbor classifier. So we look at these topics in the next session.